Hello and welcome to Refactoring Bitcoin. Today I want to implement the outputs function of the transaction class. So I take the function declaration, put it into my implementation file, and since it's a member function, I have to add the right scope. And inside the function, I will create an output. I create the result type, I call it result, and here I will add some conversion, and in the end I return my result. Okay, but what actually is a range? A range can be anything that has a begin and an end. The most simplest case would be a vector. So let's start with that. So I change the return type to return a vector of transaction output. Okay, but of course I also have to change it in my implementation, and that becomes tedious, right? Because I have to always change it in 3 different places. So therefore I add a using declaration, an alias, say using outputs type is a vector of transaction output. And then I'm going to use that outputs type in the function declaration and also in the function definition and inside the function. And we see in the squiggly lines that inside the function that outputs type can be resolved, but not in the function declaration because it's a nested type. So I also have to add the scope here, and now it's found. Actually, if I use a trailing return type, let's say auto outputs, and here in the trailing return type, I add the outputs type. This one is also evaluated in the context of the function, and therefore the scope here can be omitted. Okay, so now we want to see how we convert my the transaction outputs from the Bitcoin Core implementation to the transaction output type of my API. And to do that, I define a conversion function for a single element, and then I will use that conversion function for multiple elements. So my single conversion function is simply a function called convert, and the type of the function, the argument type of the function, I have to look what is in this transaction. I see here that the outputs are stored in this variable called vout, which is a vector of ctx out. So I define my function. So it takes a ctx out and it returns a transaction output, which is the type of my API. And inside the function, I want to add a debugging statement, just printing something that it's doing something. Here's a typo. So I execute std cout, and I just print a convert. And then I simply return a default constructed object. There's a problem here because this transaction output does not have a default constructor. So for the time being, I just add one, just default. Now it looks like this convert function will compile. So I start converting the elements in a loop. So I use a for loop for auto with an iterator. I initialize that with the beginning of the container, And I said the container is this v out here. And I can access that. Okay, this is in a member variable. This was the pimple, which is also a pointer. You see here above that the implementation contains this transaction. So I type tx, and then from tx, I can access this vout. And I will get the beginning of that. And I run the loop until the iterator does not reach the end. I will need to repeat all that, but I can also use a helper variable. So I define a variable as a const reference. I call it vout, and which is simply the whole thing that gives access to the member variable of the transaction object of Bitcoin Core. And here I simply use vout begin, and then I can run the loop until the iterator is not until it reaches the end of vout, and of course I have to increment the iterator. Now inside the loop, I dereference the iterator, which will give me this ctxout object, and I pass that to the convert function, which will give me my transaction output. And since my outputs type is a vector of this transaction output, I can here call result dot push back, and I push back the result of this conversion function. So that looks like it will compile. Let's try. I go to the build directory, make btck, and it looks like this is compiling fine. Cool. But if you pass that, if you give that to a code review, what's the first thing that people will tell you? They will tell you that if you run pushback inside a loop, you very likely want to, you're iterating, you're reallocating memory over and over. And since you already know how much you will need, they will recommend you to reserve enough space in the container. So we can call result dot reserve, and the size will be vout dot size. Okay, so this will do the same thing, but just faster, right? But reserve usually is used as a hint to reduce the number of allocations. But in this case here, we know exactly how many elements we have. So instead of creating the outputs, reserving enough memory, and then pushing back all the types, we can also initialize the outputs vector with an exact size. And then instead of calling pushback, we use an output iterator. So we call it out, and this will be the beginning of the result vector. Begin. And now inside the loop, instead of calling pushback, we dereference the output iterator and we assign to it the result of the conversion. And of course, we also have to increment the output iterator like this. Okay, this still looks good, right? It looks like it will compile. But there is actually an algorithm in the C++ standard library that does exactly that. So instead of that for loop, we can use the algorithm called transform. So this is transform, and we pass it the begin iterator of our input, the end iterator of our input, then the begin iterator of our output and a conversion function, which is just convert. And then we can get rid of the loop, and we can also get rid of this temporary variable here. Okay, so it's a nicer way to avoid for loops and use standard algorithms. But we can simplify more, right? We can, instead of the old iterator-based algorithm, we can also use the range-based version of transform, which can take two iterators, but we can also pass just a range as the first argument. And yeah, that simplifies it even more. But all of this micro optimization has a fundamental problem, which will become apparent when we look at how the function will be used. So let's say in our test case, all we care is just the number of outputs. Okay, so we have tx and we get the outputs and we run dot size. And we want to print that. So it's the cout. So we print the size and the new line. And of course, we have to include the right header. Like this. And now we want to run that. So go to the build directory, build the test executable, make btck test. Okay, that compiles. And now if we run it, we see it executes convert and another one convert, and then it outputs 2. So that means if you look at the code that we have written, it runs this very nice, nicely optimized transformation. It reserves enough space. It converts the elements, and then it takes the size and throws away the actual result. So this is a little bit annoying, right? We want to have, we want to save the unnecessary work. But there is another way. Another way to transform this that is introduced with C++20 is the transform view. Let's say we have this vout and we pipe that to a transformation. This is called, let's say, how is it written? Std views colon transform. And here we just pass convert to transform. And compiler will complain that the result type is ignored. So we store that this is stored in a variable called converted. Okay. And now from this converted, we can get the size, and we also want to print that. So let's say we print converted. Converted dot size with a new line. So we run, we execute the build, we run the build, then we execute the test, and we see that it gives us the number of elements without actually calling convert, and then afterwards we have the normal conversion that gives us then the output from the test. Okay, so apparently this view here can give us the size without calling the transformation. And I can also show something else. Let's comment out this transform function here, and I just call converted.front. And if I compile and run that, and I run it, I see if I just access one element, it also executes the conversion function only once. So this is a nice lazy approach. This is actually what we want, right? This is what we want to return from the function rather than a vector. So I get rid of all this here and I just return the converted. Return converted. This obviously will not compile, right? Because this is not the right type that we are returning from the function. And the function declaration still says we will return a vector. But this is expected. And I can actually make use of that because the compiler tell me what the actual type is that I'm trying to return. And I can then take the type from the error message and copy it into my declaration. And to make that error message slightly more readable, I simply say the expected type is int for the compilation. So this can be simplified a little bit more. This variable vout is only used in a single place now, so I can save some space, and we can get away of this temporary variable. This is actually also not needed, and instead of a local variable for converted, I can directly return. Okay, so we return. This is just what we return. And now we compile because we want to know what the actual type is. Say make btck. And here we have a nice error message. The compiler says no viable conversion from blah, 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 blah to function return type outputs type, also known as int, which is okay. This is exactly what we gave to give a nicer, to give a shorter error message. I set the return type to int. But now let's look at the error message, what it tries to convert from. It says returned value of invoke result, blah, 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 some very internals. And here we have the AKA. So what the compiler tries to return here is, I can copy that here, transform view, blah, 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 until the next backtick. And I copy that and put it in my declaration like this, and I format it, and I fix the namespace. So this is in the namespace ranges, and the ref view is also in namespace ranges. And the allocator is the default, so I can remove that. And I can now see what the return type actually is. So if I read that from inside out, I see that it is a vector of tx out, and this one is wrapped. This vector is wrapped in a ref view that is const declared. So it's actually a the vector is taken as a const reference, and this again is wrapped in a transform view, and it's transformed with a function which is passed here as a pointer, and the argument is a tx out, and the return type of the function is a transaction output. But there's a problem, right? This is actually leaking the implementation detail, right? This is exactly what we have in the implementation. And problem here is that you remember in the talk about C++ terminology, I said what an interface is. And I said that an interface is anything that clients are allowed to rely on. And therefore, I don't want to have this type as part of my interface because I don't want clients to rely on that type because that type encodes my complete implementation. And I want to reserve the right to change the implementation. I mean, that's the whole idea of refactoring. So this is not the goal yet, okay? This is not what we want to expose in our API. But It's the behavior that we want to have in our API. So in the implementation, we want exactly this here. Um, so if you want to know how we can wrap that to hide the implementation while giving the same ability, right? By giving the clients everything that they need, right? So then we give them the ability to iterate over the range, get the size without calling the actual transformation, and still being able to access all the elements. Um, if you want to know how we implement this, wait for the next video. Thanks for watching and goodbye.